9-7, linearizing data to find models. So I know this is my third take on this, but I've gotten it right now. So what does it mean to linearize something? It means to take data and perform some operation to make a linear pattern, make it into a linear pattern. In this case, we'll be taking logs of either the inputs or the outputs and turning that curve, that log pattern, into a linear pattern. So if you look on page 600 to the page 601, look at the green graphs. We're turning something curved into something straight and linear. What is something we can do with linear data? Like, why would we want to do it? We can predict using our linear patterns. We can find regression lines with a much more reliable format or method to find linear regression lines. And we can also use correlation coefficients R, and R is more accurate than R squared to determine if it is a best fit model. So we can actually tell, okay, are we close to the real thing or not so much? And do logarithmic relationships produce linear data? No, but if we take the log of something, so this is a log pattern, if I take the log of this pattern, then I can turn it into a straight line. Not all the time, sometimes it works, sometimes it's not the best fit model, but it looks kind of close to it. So we'll see an example 1. Please read all of 600, pause this, read it, come back. Okay, so for example 1, they're giving us this format. They want us to find this model using the data on page 600. And if we want to make it linear, we're looking at slope-intercept form. So I need to compare them. K and B are my y-intercepts. A and M are in the same position for slope, which means x is being related to log base b of 10. The book uses base 10, or log base b of t, sorry. The book uses base 10 for this log just because it's a common base. So we're going to do 10. You could use whatever base you want, but to follow the book to make sure we have the right answer, please use base 10. So in my lists, stat edit, I have my t, I have my p, and then in list 3, I'm taking the log of list 1. Okay, so this is now my log of t, and that's my p. So when I do my linear regression, I need to do linear regression of list 3 as my input and list 2 as my output, because I'm changing what the input looks like. Instead of just plain old x or the t values of 1, 2, 5, 10, 15, 20, 30, I'm taking the log of 1, 2, 5, 10, 15, 20, 30. So stat, go over to calc. You can do 4 or 8, it doesn't matter. I'm doing list 3 versus list 2. If you don't do that, it's going to turn out to be wrong numbers. Store regression, there's your shortcut. If you have the long way, hit bars, y bars, function, and hit y1. Calculate, and you should end up with what the book gave you. So read your book. I did rewrite it down here, but it took me 3 tries. So that's part A. Part B is to predict the amount of study time needed for the mean percentage of word meanings recalled to exceed 95%. So I need it to be greater than 95% out here. So this needs to be greater than exceed. So it has to be greater than. Cannot equal 95. Has to be greater. Okay, 2 ways you can do it. You can do it algebraically, or we can do it with the graph. So on the graph, we'd look at the table to see what do they want to do. They want to actually solve it algebraically. So you could go in your table, second table, and go until 95 is going to be between 1 and 2. So I know it's going to be some decimal. You could break this down farther and see where it is, or we can do it algebraically. To solve for x, I need to subtract 30.093. So 95 minus 30.093. Yep, I can scroll down. There you go. And that's going to get me 64.907 less than 36.167 log of x. Divide by that, so divide by 36.167, so I get 1.79465 is less than log of x, which means, and this part's strange because of the less than sign, so I need 10 to the power of 1. Ooh, that's better. Okay, we're going to leave this less than alone, I'm going to take the log of both sides. That didn't work as much as I wanted it to. Because the log of that wouldn't work. Okay, so if I write 10 to the 1.79465 is going to be something to the x log. So if we think about this, if I have like 5 that goes into that, log of the value of x has to be greater than that. It's between 1 and 2, I know that. So if I do 1, log of 1 will not be greater than that because it's not greater than 95. So that would have to be 2, so it has to be, x has to be greater. So I'm keeping the greater than. Yes, okay. And now if I do 10 to that second answer, so x has to be greater than 62.32. And the book did some rounding in there, so it has to be greater than 62.32% for it. Or not percent, that's not percent, we're looking for seconds. All right, that's our answer.